right, so thank you very much for having me. It's a pleasure. I'm very happy to have been invited to this beautiful conference. So I'm very grateful to the organizers. So this is joint paper with Johannes Scherr from the University of Bristol, and it's very, very much work in progress. It's only the second time I present this, and also Johannes and I essentially changed the paper shortly before this presentation, so it's very unstable material in a way. So essentially, I will connect this to the outline paper, but I won't have to work much to do it because the true theoretical part has essentially already been covered by Kripke 50 years ago. So he left us free to wander around and focus on other things, in particular quantifiers in the supervaluational framework. Full disclosure, I'm not a supervaluationist. I think probably Johannes is a bit more a supervaluationist than I am. But I think that supervaluation semantics is very interesting to explore. So this is what I will try to do. So as it has been pointed out many times during this conference, as also a matter of historical truth, I think it's difficult to overestimate the influence of the outline paper. I would like just to draw your attention to a couple of, if you can move the microphone, like to draw your attention to two reasons, not the only reasons, but two that are relevant for what I'm going to say. Namely, that Kripke's approach is modular. There's in the sense that there are a lot of moving parts. You can change the base language, the base models, the base theory, as we saw in some of the talks yesterday. You can change the logic that you use for the jump operator, and you can change the consequence relation. And you can play around with a lot of these combinations, which is also exactly one of the things that you're doing here. And it's also relatively easily extendable. Some extensions are not easy, some extensions are easier. But as someone said yesterday, in this, I think it was Michael during the talk, Kripke's construction features in almost all approaches to self-applicable truth, exactly because you can embed it relatively easily into a variety of other approaches. And these two aspects are exactly the two aspects on which the work that I'm going to present depends on. So it tries to present a variation and an extension on Kripke's original approach, in particular, the supervaluational variant of that. So the overall goal of this work is to provide a framework for quantifier semantics in the presence of indeterminacy. Indeterminacy here means something slightly different, but possibly connected with what Lavinia was mentioning before. Here, I have in mind specifically three potential sources of indeterminacy, namely presupposition failure, vagueness, and semantic paradoxes, ill-foundedness, and related phenomena. So indeterminacy here is just a very generic term for what goes wrong in vagueness, presupposition failure, semantic paradoxes, and so on. So what we want to do is to extend relatively standard or slightly generalized supervaluational semantics and supervaluational treatment of these three sources of indeterminacy to the cases of generalized quantifiers. So rather than, so this is what I meant before, Kripke provides an excellent blueprint on first order language, but there's a lot of things you cannot say in a first order language, and notably a lot of quantifiers cannot be defined in them. So we try to extend a Kripkean treatment to generalized quantifiers. We obtain two competing semantics, and we still don't quite know which one is best, if any. But both these semantics, they diverge substantially in some of the results, but both of them can satisfy at least some desiderata concerning these three sources of indeterminacy, which we think are important, and in particular can recover a substantial fragment of generalized quantifier theory, which I'm going to relate. Okay, so this is the plan. And these frameworks are designed to be compatible with Kripke's treatment of self-applicable truth. In particular, I have this one slide that said that if you like this framework, it is immediately compatible with a Kripkean treatment. I also have more slides if you're interested. Okay, so here is the outline for today. So as you can see, the talk stops there. If some of you are interested in some more details, we have some appendices. So if you really want to know more on quantifiers to the point that you're willing to skip lunch, I'm more than happy to discuss these three things. All right, let me begin from a very general picture on concepts, high order concepts and indeterminacy. So I'm going to start with a Phlegian picture. I do not claim any interpretational accuracy. I'm not sure whether Frege thought exactly in these terms. Most likely he would have phrased things this way. But a Phlegian picture is one where concepts can be understood. A Frege-inspired picture is one where concepts can be understood as functions from individual truth values. And higher-order concepts are functions from concepts with truth values. And quantifiers can be understood as higher-order concepts, so as these sort of functions. So, for example, you might think that every is the function that, given, say, the concept dog and the concept friendly as input, outputs true if whenever the concept dog applies to an individual, so does the concept friendly. So it's a relation between concepts. Now, this is the classical picture, I would say, but if you allow some indeterminacy to sneak in, then things change. So in a completely indeterminacy-free world, concept C applies to an individual or the negation of that concept does. But of course, if you have indeterminacy around, this is no longer the case. These can be interpreted in a variety of different ways. We are going to stick with the simplest, I believe, namely a partial interpretation, where partial means trivalent, three-valent. So you basically only have cases where a concept applies, or the negation of that concept applies, or there is a gap. The gap is not structured in any way. You can structure it if you want, but this is the simplest implementation. So a concept is a partial function. So of course, the usual complaint about a trivalent treatment of indeterminacy is that it is too simple, perhaps, or at least it presupposes that one can unproblematically separate three cases, right? The cases that are not indeterminate, so either the concept applies or the negation of the concept applies, and the cases which are indeterminate, namely the gap, where neither the concept applies nor negation. But this might be not always guaranteed. And the usual supervaluational remedy to this situation is considering not just one partial interpretation, so you have one tree partition, but you actually have many. And typically many means that you already have some semantic information that maybe provides an initial tree partition, and then you refine it by looking at what goes on in all the ways of refining this initial tree partition, which is basically the kind of picture that we adopt. We just want to apply it to generalized quantifiers. So essentially, ultimately, this boils down to combining two strategies for handling indeterminacy, which is the usual or one way of implementing the usual supervaluational strategy, combining trivalence and quantification over these interpretations, named supervaluations. Okay, now back to quantifiers. Quantifiers can be partial too, right? I mean, presumably, classically, every dog is friendly is true in a given interpretation if whenever the concept dog applies to an individual, so does friendly. Okay, but now we have cases in which this is not enough. Supervaluational truth requires considering all possible interpretations, right? So it basically means that this subset relation has to be preserved across all the interpretations that refine a given one. So every dog is friendly must hold, in the sense specified by the first bullet point, in all the interpretations that refine or extend a given one, compatible with the given one. So classically, every dog is friendly is false if it isn't true. But if you have partial interpretations around, it can happen that you have an interpretation in which dog is not a subset of friendly, and yet there is no single individual that is both dog and not friendly, right? Because now the, let's say, extension and anti-extension do not exhaust all the individuals. This can happen. And so this means that you also need separate falsity conditions for quantified sentences. Okay. Now, this is the general conceptual background against which we want to motivate our formal semantics. I'm going to focus the presentation first on the quantifiers. Then I will say very little about adding truth, because as I said, fortunately, Kripke did all the heavy lifting for us. But then I will go back to applying the semantics. Okay, so the setup is a slight generalization of supervaluational semantics. Take a first order language. For the moment, we do not specify further. We will in the future, but for now, pretty much any first order language will do. An interpretation is what you would expect as far as individuals and functions are concerned. You take an empty domain, and then you send a term to an individual and a function to a function constant to a function. A predicate is now sent to a pair, and this is because we are going to consider extension and anti-extensions with possibly non-empty gaps. And the requirement is that these two components do not overlap. So we send a predicate to a pair, think of it as an extension anti-extension pair, and you just require that these two things do not overlap. If you want to allow them to overlap, maybe going into a paraconsistence or dialectic direction from the get-go, you can do that. There's nothing in the machinery that prohibits that. We just start from this assumption. Okay, the set of interpretations is that int d. So any interpretation might be partial. So we do not assume that the extension and anti-extension, if you take them together, exhaust the domain, as per what I said before. And also one important thing, this is really the beginning of the supervaluational machinery. If you have two interpretations, we say that J extends I if basically it's pointwise extended in both extension and anti-extension, right? So the positive component of J is a superset of the positive component of I applied to P, and the same goes for the negative one. So it's a refinement. One thing that we do not assume here and throughout is that once you take an interpretation and you extend it, you end up with a total one. This is not assumed. It can happen, but it can also not. Right, so once you have this, you can define supervaluational structure, which can be perhaps more briefly also described as a bit of a modal structure, as it is sometimes done. Take an empty domain and take a set of interpretations. For simplicity, we assume that the interpretations agree on the terms. So they will disagree about predicates, presumably they disagree about what counts as friendly, but not about denotations. Denotations are always the same. And we have a relation on this interpretations, which basically includes these extension relation, right? It's reflexive, transitive, and also includes this extension relation. One way of looking at it is that basically your interpretations are worlds, and this is an accessibility relation, right? You have a modal structure. It's one way of looking at it. Right. Now, we now need to talk about quantifiers, and this is a little bit more abstract, but because we are going into this high order concept business that I was mentioning at the beginning. So first, let's define the space where our quantifiers live. They live on this domain, which we denote on domains of superscript n of n, and it's basically the function space between the interpretations and sets of individuals. So because we want quantifiers to be sets of pairs of functions, as opposed to generalized quantifier theory in the classical extensional frameworks, where a quantifier is a set of pairs of sets, because this is the Fregean version of that. So the domain is that the general domain is just the union of all these function spaces. Okay, and a quantifier in general will be a subset of a relevant Cartesian product of those domains, depending on the type of the quantifier. So we are going to only consider the so-called type 1-1 quantifier. You can think of type 1-1 quantifiers in the usual extensional setting as basically taking into account relations between sets. Okay, so like every dog is friendly is the subset relation between individuals, dogs and friendly. So in general, a quantifier like every, I cannot write, but a quantifier like the screen.
It's behind the screen.
That's behind the screen. Just a quantifier like every is traditionally represented as a set of order pairs A, B, such that A is a subset of B. Okay, so a type 1-1 quantifier works in the same way as far as, living in this subspace, but now it's going to be a set of pairs of functions as opposed to a set of pairs of sets. Okay, it's a minor reformulation. There isn't anything very substantial at the moment, and we're just going to focus on these type 1 quantifiers. The reason we are going to focus on type 1 quantifiers will become a bit more clear, I hope, after we consider the conservative quantifiers, because these are really the focus of our attention. In our framework, you can express conservativity like that. Basically says that a pair Fg belongs to the quantifier just in case the pair F intersect G belongs to the quantifier. You can think of it as a quantifier that repeats the first argument or the restrictor in the second argument, like the scope. So for example, every is a conservative quantifier. If I say every dog is friendly, it's equivalent to saying every dog is a friendly dog. Some bike is red is equivalent to saying some bike is a red bike. Most streets are empty is equivalent to most streets are empty streets, and so on. So you can test this intuitive equivalence by just repeating with a conjunction the second argument. And this is just to zoom in on our topic. Our topic is conservative quantifiers. So let's define cons subfactor n as a set of all the conservative type 1 quantifiers over this basic structure. And the main reason why we focus on conservative quantifiers is their linguistic prominence. They're very important because the customary analysis is that they are the interpretation of determiners in natural language. So they appear a lot in natural language. And also there is a sense in which type 1 quantifiers that are familiar from first order logic, everything, something, and so on, including quantifiers that are also not definable in first order logic, like infinitely many things, have this feature of being expressible with this quasi-logical thing or things, which can be seen to be a special case that. So everything is, I don't know, blue, is like everything that is self-identical is blue. So you can express that as a type 1 quantifier just by making sure that the first argument is something that is true of every individual. Typically, you can put x equals x or something. So they're linguistically very prominent. And in general, if you go higher up in the hierarchy and consider type 1, 1, 1, or type, I don't know, n1, n2, n3, where n1, n2, and 3 are numbers, it's not easy to find natural linguistic correlates of these quantifiers. I mean, some have been found, but in general, you do not have a very simple and straightforward identification of a very large class of natural language expressions with one of these elements in the hierarchy, but for type 1 and type 1. And since the type 1 are a special case, we focus on the type 1. There is also another very important reason why we focus on type 1 quantifiers, which is the so-called conservativity universal, which is a empirical thesis, essentially, that says that the quantifiers that we find occurring in the wild, in nature, in natural languages, are the determiners that we find in nature are interpreted by conservative quantifiers. So you can cook up a non-conservative quantifier, you just write down a formula that basically doesn't satisfy that equation there. But the ones that you would find ordinarily in natural languages are conservatives. As far as I know, Michael, of course, can tell me whether I got this wrong, but as far as I know, this universal has been first proposed in the 80s and has been tested extensively since. And very few putative counter examples have been discussed. The most famous is probably only, which is non-conservative. But the consensus seems to be that only should not be treated as a determiner, because only modifies places in phrases, in sentences, that no determiner can modify. If you take the sentence, I saw them on the train, you can insert only pretty much everywhere in that sentence. Only I saw them on the train. I only saw them on the train. I saw only them on the train. I saw them only on the train, and so on. No determinant does that. So the consensus seems to be that only is a polymorphic modifier, I think it's called, but not quantifier. There's a paper that came out recently in the Journal of Semantics that disagrees strongly with that, but I will not enter this debate and I will assume that only is out of the scope. So this motivates the restriction to conservative quantifier. Okay, good. Now we have our object of study. conservative quantifiers in this framework here. There is a beautiful theorem by Keenan and Stavy, 1986, that provides a very simple and elegant characterization for all the conservative type 1-1 quantifiers. Not quite in this framework, in the extensional or lambda term framework. And the gist is that each of them can be defined by applying Boolean operation to just 3 kinds of type 1-1 quantifiers, so-called basic quantifiers. Here I am already misrepresenting the theorem because they do not say it can't be defined. This is the use that I need to make of the theorem. They just observe that the set of conservative quantifier is extensionally equivalent, is the same set as the set that I'm going to present now, which is basically the result of closing the basic quantifiers under Boolean operation. We are going to use their result as a definability result. So this is why it's important for our purposes that they can be defined by applying Boolean operations. Okay, but I was getting ahead of myself. The basic quantifiers are every, the so-called cardinal quantifiers. You can take at least lambda many for every cardinal that basically is up to the cardinality of your domain. Okay, and possessives like John's. So basically it means that for every element of your domain, you can have a name, and then you can have the basic possessive related to the term that denotes that concept. So these are your basic quantifiers. And the result that Keenan and Stavy have is that if you take these quantifiers, they're not just 3 quantifiers because you have a lot of cardinals, a lot of individuals, but there are 3 kinds of quantifiers, and you close them under complement and union or intersection, doesn't matter, then the set that you obtain is the same set as the set of the conservative quantifiers. So as a first step to recover an amount of generalized quantifier theory in our framework, and so to be able to give truth supervaluation of truth conditions for the conservative type 1-1 quantifier, we can establish a version of the Keenan-Stavy theorem for it. So what we have to do is to give the extension of the basic quantifiers in our framework, to give the Boolean closure, and to prove an analogous version of the Keenan-Stavy theorem. So suppose you have a supervaluation structure and isolate the set including the denotations of every, at least lambda many, and the possessives. This is the denotation of every. Essentially is the set of pairs, Fg, such that the subset relation holds for all extensions. Okay? So take an arbitrary interpretation and take all extensions of that interpretation, check whether the subset relation is preserved. If it is, then the relevant pair of functions is in the denotation of every. So this is basically the usual denotation of every, the subset relation, but made supervaluation, namely quantifying over all possible extensions of every given interpretation. So for those of you who are already familiar with generalized quantifier theory, you're presumably already familiar with this bit here, but you just quantify. Okay. At least lambda many, pretty much the same. It means that the things that are F and G are at least as many as lambda, but again, you quantify for all J prime extending J. And finally, this is the usual possessive. So this is the possessive relation, the things that are John's, say, and our F are also G, okay? But again, the usual possessive relation is quantified along all possible extensions of a given interpretation. So this is the set including the denotation of every, at least lambda many, and the possessives in our framework. Okay. Now we just define the Keenan-Stavy operations, namely the Boolean complement and the equivalent of the meet. And of course, this is the generalized version of the meet. And once you have that, you can define the class that they prove in a purely extensional framework to be extensionally equivalent to the class of conservative type 1-1 quantifiers, which is what they call D. So we also call it D sub M. And D sub M is the smallest set that contains the basic quantifiers in our sense, so the sets that I showed you before, and it's closed under the complementation and the generalized meet. So whenever you have a quantifier, you also have its complement, and whenever you have a set of quantifiers, you also have the meet. Okay, so this is our set D sub M, and the theorem that they proved is that that their theorem, we just use the supervaluational structure, that they are the same set. Okay, so the set of all the conservative type 1 quantifiers is the same set as D. Okay, now the one direction is relatively straightforward. You just have to check that what you have here is conservative and what the operation preserve conservativity, basically. The other direction is more laborious. So here we adopt a strategy that is outlined in the paper that Michael and I wrote 100 years ago and hasn't yet been refereed. And the nice thing about this, I think, is that the proof that is there is basically a purely algebraic proof. So it doesn't deal at all with the set theoretic structure, unlike some aspects of the original proof. I mean, the original proof contained, it was possible to distill the algebraic structure, but this proof is purely abstract. And so since the structure of the relevant algebraic structure in the extensional case and in the function space case is exactly the same, the beauty of this is that you can just apply the same proof template. It works exactly the same. And here I'm not going to get into the proof. When the paper comes out in another 100 years, you can look it up there. And the trick is that you look at this set and you observe this is a complete atomic Boolean algebra, and you can characterize the atoms as specific quantifiers. I'm not going to tell you what quantifiers they are, but you can characterize the atoms as specific quantifiers, and the atoms can then be defined as Boolean combinations of non-atomic quantifiers. So you take the big quantifiers and go down to the atoms. These are denoted S and W. And finally, S and W can be defined by the quantifiers in the basic ones. So you take the basic quantifiers, you define these two quantifiers here, and then once you have these two quantifiers here, you have the atoms, and since it is an atomic Boolean algebra, once you have the atoms, you have everything. So this is the structure of the proof, it's purely algebraic proof, so it lifts immediately to our framework. Okay, good. So now we have a version of the Keenan-Stabi theorem, which gives you the conservative quantifiers, but also gives you a way of defining the conservative quantifiers. And in particular, in order to give truth conditions for the conservative quantifiers, in virtue of this result, all you have to do is to give truth conditions for the basic quantifiers, and then give truth conditions for the complement and the Boolean generalized union or intersection, and then you can apply the Keenan-Stabi template to get all of them. So this simplifies the task drastically. And yeah, this is what I said. To prove results about a conservative type 1 quantifier in our framework, we use the Keenan-Stabi theorem as a definability result. So we assume, so now since it is a definability result, it means that these quantifiers are formulas in our language. So we now need to be a bit more specific about what language we consider is not going to be any more a first order language, and it has to have the suitable elements to write down formulas whose extension is the selected quantifiers. So we assume that the logical vocabulary includes the basic quantifiers, every at least lambda many, and the possessive quantifiers for all the individuals and for all the cardinals up to the cardinality of the domain. We also require infinitary conjunction, because remember, we have to model the generalized meet. So the size of the conjunction is going to depend on the model. So you fix a supervaluational structure, so everything is going to be relative to a structure. This is no surprise in quantifier theory, because quantifiers have extensions. And the cardinal kappa, which is greater than that. And this has to be for the very deep philosophical reason that otherwise it doesn't work. So you fix a cardinal that it is at least as large, and you take big conjunction to be of size at most kappa. Okay, take standard negation. Formulae are defined as expected in the infinitary language. So it means that you can have infinitary conjunctions with conjuncts which are also infinitary conjunctions and so on. Okay, so now in order to define semantics, we do the usual steps. An assignment is a function that assigns objects in the domain to variables of the language. A variant is one that disagrees with just one individual. And the denotation is pretty much what you would expect. So it's either whatever you assign to a variable, if you're looking at the denotation of a variable, otherwise what you assign to a constant, and otherwise what you recursively compute when you have a function. Now, we can now define truth in a supervaluation structure. So suppose you have a supervaluation structure, one interpretation, one variable assignment. This is all relatively standard. So positive and negative extension predicates are defined as you would expect. Identity is classical. If you have a sentence that is a doubly negated sentence, you just look at the non-negated sentence, and conjunction works in the strong-clean way, as you would expect. So nothing fancy here. What is a bit more laborious is to write down the supervaluation truth conditions in this sort of strong-cleaning-ish way for quantifiers, which are like that. You have already seen some of them. Maybe you have seen this, right? It's a subset relation for all extensions of the given one. The negative clause is basically just the existence of a witness. So when it is false that every A is B, where you have one individual that is every B is C, when you have one individual that is B and not C in the non-classical negation that you have. Okay. Similarly for at least lambda many, you have preservation of at least lambda for the conjunction, but you have to have a witness. So you've got to have at least lambda many, B or C is false. If you have something in here and in here, things that are not C and not D, sorry, that are not C and not D, they are less than lambda. And similar story for this. This is basically the version of the supervaluational clauses that is compatible with K3. So essentially, we do not postulate that whenever you take an interpretation and extend it, you end up with a classical one, because it could still be partial. So this is roughly K3 supervaluation that Johannes, my co-author, has developed in independent work. And this is the relevant bit for quantifiers. Okay. Now we have truth conditions, or satisfaction condition for quantifiers, adding truth. I have one slide here because, as I said, Kripke did all of the heavy lifting. If you want to know more, I have an appendix. But the one thing we need to know for now is that everything I said is compatible with that form of naivety. It's not, in general, going to be compatible with stronger forms of naivety, such as intersubstitutivity. This is supervaluational semantics after all. But you can, once you suitably code sentences, and I haven't told you how yet because you have an infinitary languages, so it's non-trivial. But once you suitably code up languages, sentences, and you add the truth predicate to the language, you can prove that there is at least one supervaluational structure, which is itself fixed point of a suitable kind, that witnesses the naivety of truth. Much in the same way in which you would have weak naivety in the supervaluational semantics for Kripke's original construction. So that feature is preserved. And the reason that feature is preserved is that in those conditions, you can basically still apply the usual monotonic jump operation. You apply Visser's theorem from 1989 that generalizes the Tarski theorem. Okay, so for truth, we basically have our formal semantics. Our formal semantics is compatible with truth. Now we are going to ask ourselves, what kind of theory of quantification we got? So we have truth conditions. We know that from those truth conditions, we can define these conservative quantifiers. But we have the following situation. The classical type 1-1 conservative quantifiers are the same set of quantifiers as the ones you classically, the set you obtain by doing the Keenan-Stabi stuff, starting from a classical model. Here we have the same thing, but for a supervaluation. So we have two sets are the same in the classical universe, and two sets are the same in the supervaluational universe. They're not the same set, if you cross universes. So what we have to check, and this is provable, what we have to check is what properties they have. So we have to test our semantics on some well-established grounds. So we wanted to test it on monotonicity properties. They do not tell us all there is to know about quantifiers. If you take a book on quantifiers, they're typically a relatively big portion of that book. It's an important testing ground, I think. So how good is our semantics at recovering classically valid inferences involving generalized quantifiers? Now, in order to test our semantics, we need at least two things: a notion of logical consequence, because we need to test inferences, and also a well-understood class of inferences as our target. Now, the notion of logical consequence that we adopt for the moment, we're going to change it in a few slides, but for the moment, we adopt a local consequence relation, which is the usual consequence relation. So gamma locally entails A if for every supervaluational structure and interpretation, if every sentence in B in gamma is true, then A is true. So you have just one quantifier. For every M, truth reservation. Okay. As for B, as I said, we test our semantics on monotonicity properties. Monotonicity properties basically connect the behavior of a quantifier and the subset relation. The simplest one is probably the transitivity of every, right? Suppose that every A is B, and you also have that every B is C, then you also have that every A is C. So we know that every certainly has this monotonicity, right? And you can test a lot of them. Right, here you write an arrow to the left if the relevant monotonicity property concerns the first argument, right? The restrictor. And you write it to the right if it concerns the second argument. You write it going up, so upward and tailing, as it said, if you are looking at the subset relation, and you write it pointing downwards if you're looking at the other direction of the subset relation. Okay, so this is just a definition of the monotonicity properties, and they mix as you would expect. So there are quantifiers, for instance, that are both upward and tailing in restrictor, so to the left, and upward and tailing in scope, and so on. And this is just standard off-the-shelf textbook definition, nothing creative here. And we also know of many, this is just a simplified, just a fragment of this, but we know that there are many GTT-bound relations between monotonicity properties that concern the behavior of negation. It's very important for us. We only consider outer negation. In the literature, you find a lot of inner negation too, and duals, but we neglect. Okay, so we have our testing ground. We're testing ground monotonicity properties. Why do I say that they are a good testing ground? Because the subset relation here is presumably expressed by every, and every is a sentence in our language. So we can check whether the formula that defines this quantifier in the Keenan-Stubbe way, together with every A is C, okay, which is also a formula in our language, locally entails the formula that defines the first quantifier for C and B. So we can transform those things into inferences and check whether they're valid in our semantics. And we have, we have a standard against which to test them, the classical monotonicity properties. Now, I'm going to argue that the results are mixed at best. And in particular, you do recover some expected forms of monotonicity. This is the monotonicity of at least kappa many. It behaves as expected, is upward entailing in both restrictor and scope. This is the classical monotonicity property of cardinality quantifiers, and it's recovered here as a corollary because by the Keenan-Stubbe theorem, for free, you have the right monotonicity property for some and for infinitely many, which are all definable, right? But for other quantifiers, you do not get the right monotonicity property. If you want to say, if you want to test not at least kappa many, you do not have the right monotonicity property. Negation should flip both arrows here, and you do not get the right monotonicity property. As a result, you also do not get the right monotonicity property for no. Okay. So you can go on and do a lot of tests here, and I'm going to skip some of them. We have nice results on every, but you have mixed results for not every. You get one monotonicity property right, but the other one. So you have mixed results here. At least and every satisfy their monotonicity properties. Negating a basic quantifiers, however, disrupts the monotonicity property because we have a weird clause for negation in order to be compatible with K3 semantics. So it disrupts the monotonicity property predicted by the generalized quantifier theory. So by the Keenan-Stabi theorem, these conservative quantifiers can be defined from the basic ones by negation and infinitary conjunction. Monotonicity properties are not preserved. You have also difficulty in giving a taxonomy of which quantifiers have the right monotonicity property. It's easy to show that conjunction preserves monotonicity. So for instance, if you define a quantifier as a conjunction of two monotone quantifiers, say every person and at least two cats, that has the right monotonicity properties, but few interesting quantifiers are defined like this. Interesting quantifiers have to be checked one by one. For instance, if you want to check most, you will see that most is upward entailing in the restrictor as it should be, but its negation fails to be downward entailing in the scope as it should be, but its negation fails to be downward entailing in the scope, but it should be. So mixed results. Yeah, this is pretty much the picture. So this motivates us to look for a slightly different semantics, which I'm going to present very quickly in its outline, where you can improve on the monotonicity properties. You can improve, but it's not all rosy because there's a trade-off. You lose something. So I'm gonna end. That's why I said we end up with two competing semantics. You gain on monotonicity, you lose on something. So you can basically force the truth conditions to be symmetric. And you're familiar with Hannes Leitgeber's semantics for hype. It's pretty much what goes on here. So you have a hype-like modal space. So everything is defined exactly as before. Okay? Interpretations are defined as before. The set of interpretation is always the same. Now you just single out the ones that are consistent and the ones that are complete. Okay, so you can have consistent interpretations and complete interpretation. The ordering relation is defined as before. Now, in order to have a hype-like structure, you got to have the Raouli star. So you have an operation that does exactly what you would expect from the Raouli star. So if you have an interpretation applied, the positive part of an interpretation applied to a predicate, it gives you the things in the domain that are strictly positive or neither strictly positive nor neither positive nor negative. And the negative, the application of the Raouli star to the negative part of a predicate is exactly the same but dual. And now, using the Raouli star, you define a variant of supervaluational structure. You define a symmetric variant. So everything is as before, but in addition to the set of interpretations, you have its Raouli counterpart, and you also have the Raouli star itself. Now, interpretations agree on constants, so on terms, nothing strange there. This set, X star, is the star of every interpretation in X. And now your accessibility relation is defined on these two, right? So you take the union of the interpretations and the Raouli star dual, and you have an accessibility relation with reflexive, transitive, and convergent, just like hype, okay? Which is essential because otherwise you do not get nice negation conditions. And then you have these other things that are not especially illuminating, but they're necessary to make it work. Okay, now using this supervaluation structure, what we can do is to deliver, yeah, this is basically inspired by Kripke's system. What you can do is define much, much simpler truth conditions. So take a KS3 supervaluation structure and interpretation and variable assignment. You define B in true at the interpretation J in M under beta in symbols M and J force A of beta if the same positive conditions hold. So the positive clauses are untouched, and there is just one for negation, which is just the classical ones, but for the Raouli star. Okay, so basically, whenever something is negated, it means that the Raouli star of that interpretation shouldn't force the non-negated sentence. This time, for convenience, we also take infinitary disjunction to be primitive. So imagine that you also have a positive truth condition for infinitary disjunction, which is the one you would expect. Now, we need a final tweak before looking again at monotonicity. Now we need to take global consequence. So take the class of O, the supervaluational structure. Let's say that A is a global consequence of gamma if now you have a double quantification. For all structures, if it is the case that all structures satisfy every sentence in gamma, then all structures satisfy A. So rather than for all if then, you have if for all, then for all. This isn't the only candidate for a global consequence relation. If you want, for instance, to force contraposition for your quantifiers, which is something you may or may not want, you also need to add a dual clause that reverses this for negations. And this way you get contraposition. If you don't want contraposition, this is enough. Now the picture is much better for monotonicity properties. Let's say, take any monotonicity property that you like. Monotonicity up, down, left, right, doesn't matter. Let's say that Q has P in a semantics, just in case the inferences that encode P are valid in the consequence relation associated with that semantic. This is a cumbersome way of saying something simple. Take every. Every has that monotonicity property in GQT because these inferences hold in GQT, which is basically transitivity, either starting from the scope or the restriction. Okay, so every has this monotonicity property in GQT because those inferences hold. Now we're going to check which properties we have in our semantics. And the pleasant answer is all of them. So you can prove that every conservative type 1-1 quantifier, given any conservative type 1-1 quantifier and a monotonicity property P, Q has P in GQT if and only if Q has P in KS3. So the situation is much improved. Now we have all of them, right? And we don't need to test individual quantifiers and maybe expect mixed results.
So is that second one a typo?
Which one?
A, B, B, C, B, C?
A, B, B, C, A, C, sorry, yes,
Yeah.
the AC. Yeah, right. Okay, so the situation has improved, but as I said, there's always a price to pay. Okay, so this is the better picture, monotonicity type. We have all of them essentially. So these results do not yet show that the theory captures everything you might possibly want about quantifiers, right? There are other things to be tested, but at least a substantial portion of the classical theory of quantification can be recovered. And this framework here is a non-classical framework. Okay, so this is a very different framework from classical quantification theory that is consistent with weak naivete, unlike the classical framework, which is not consistent with weak naivete. And it also accommodates supervaluational treatment of indeterminacy. So if you want to give, a treatment of vague quantifiers, such as many people are here, or presuppositional quantifiers, so essentially every quantifier, and you want to show that the indeterminacy there receives a supervaluational treatment, this is all consistent. In addition, you have all these monotonicity. Now, for the trade-off. Is there a real choice between these two semantics? Now, they both offer a supervaluational treatment of indeterminacy. They both retain form of naivete, but KS3 delivers better results on monotonicity. Now, as soon as you consider further logical vocabulary, things become more nuanced. And in particular, it's easy once you have every to define a condition, right? Because you have every A is B, so you can just define the relevant conditional. By the way, let me just very quickly jump back. If you look at the truth conditions for every, it really looks like the intuitionistic condition, right? You start from a point in the world, and then you check that the subset relation is preserved at all subsequent ones. And in particular, if you want, you can really turn this into a supervaluational version of the K3 clauses for the Boolean fragment and intuitionistic conditional, if you wish. In general, so it's always possible to take all this apparatus and define a conditional connective. You can define it primitively or via every. The big difference is that K3 delivers a deduction theorem and KS3 does not. And so far as we can tell, there is no way of improving, at least within this framework, to improving on KS3 to deliver a deduction theorem. So it seems to be a genuine trade-off. You might think that deduction theorem is not so relevant, or instead you might think that it's super important for a feature of the conditional. So I don't know. this is why I said it's work in progress. I still don't know what is the best one, if there is a best one. So presumably what needs to be done is to extend the area of the testing ground. So far we have considered properties of the conditional, properties of monotonicity. As I said, another factor might be contraposition. So here in K3, you do not have contraposition. Currently, you do not have it in KS3 as well. It's unclear. You can extend KS3 with contraposition in order to deliver contraposition. Not so much in K3. In K3 supervaluations, it's unclear whether the monotonicity properties are compatible with that. Okay, so this is the overall picture. So as I said, I have plenty of appendices for those of you who are interested in the details. And for now, stop here. Thanks very much.